Hello again. How are y'all doing? All right. Awesome. Good. Glad to hear it. I just wanted to reiterate quickly, one of the purposes of this event is for everyone to be able to come and learn and hang out with each other and be awesome. If for any reason you feel like that's not happening or something weird is happening or you feel unsafe or unwelcome for any reason, just find someone in a blue shirt. They'll help you. And if you can't find someone in a blue shirt, there are people at the front desk who can help you. So our next speaker is an iOS and OS X developer who is known for breaking and reverse engineering software. He's currently working on the second edition of OS X Internal's A Systems Approach. Sam Marshall.
Right. Hello. So for my own talk, I decided to go with something that's a little bit different from everyone else. Talk about some insecure code. So what exactly does this mean? We've seen over the past few months that a lot of code, especially with cryptography, has had a lot of bugs in it that has resulted in terrible things happening. And a lot of people attribute this to the languages we use and our code review and auditing process. For stuff like OpenSSL and Apple's own security framework, this is true. But I think a lot of the issue is not in so much the languages we use, but in the fact that code is both really hard to do. Even when we're doing simple things, it's very easy to get very complicated within a few minutes of starting. With this, we get mistakes quite often. Some of these go unnoticed for quite a long time, many years. And we'd like to talk to you about two real-world cases of exploitable code that existed in software for one for many years and one for a couple of months that ended up in being quite dangerous for everyone. First comes from a company you may know of as a game studio that can't count up to the number 3, involving input handling, specifically with URL strings. Now, what is a valid URL string? When asked this question, I sort of came up with 3 general ideas. Mainly that it's going to start with HTTP, HTTPS, or a www. Now, you could validate URLs using like a regex, and that would probably get you a result from the format of the URL, but not necessarily the contents. So if you wanted to check any sort of URL input before presenting it to the user against, let's say, a phishing or malware database, so you're not giving your users bad links to click, you would need to somehow decompose these links and run some sort of analysis on them. Now, let's just take the Google About page, for example, as input. If we're going to strip out the known prefixes for it, we're going to be left with something that looks like this. And from here we can go and decompose it a bit farther and break out into an array of components of this URL. And so far this looks pretty straightforward. Like we can now take this and sort of match it against our own database and say, should we be presenting this? Is this valid? And if it comes back and says yes, it is valid, there's nothing wrong with it as far as we can see, we can prepare it and do a sanity check and make sure that, well, all domains exist. They're not going to be 0 length, so we'll just sanity check it for 0, prepare the prefixes to put back in, join up the array, and now we're left with that same input that we started with. This is rather simplistic, but it gets the job done, and when presenting to the user, you'll get the Google page. Now, what if you were to give it something that looked like that? This doesn't look valid at all. I mean, it's got this www in it, but the rest of it doesn't look like a valid URL. But let's just run it through the steps we just created for this anyway. So we've got our input, We're going to strip out the prefix that we know. Now we're left with what sort of looks like a file path. Now we're just going to split this out the same way we did before. And if you'll notice, this time we don't have a first element that has a length. It's an empty string. So that's going to come back from our database check and say there's nothing this matches against, so it looks like it's okay. But it's going to fail our sanity check. And it's now going to say we're not going to put the prefix that we took out back in. And then when we join it up, we'll get a different URL than what we started with. Now, if we're dealing with web URLs, this would still be invalid. But you'll get something like this if you run it through an open, because NS URL and CFURLref handle both file URLs and web URLs. So in fixing this code, there really isn't anything wrong with it. I mean, it could be improved a lot, but the basic logic that we have there is pretty solid. So the fix that ended up going into the software was that we needed to sanity check things that we weren't expecting to be handled in the first place. So in this case, it was a simple documentation check to make sure what we were getting was also what we were getting get back. And in the case of NSURL, that could have been something completely different based on what we were giving it in. Now, this seems like a pretty simple thing to miss, and I'm sure there's plenty of people out there with software that does something that can have something like this in it. So how do we avoid it? Double and triple checking documentation, making sure that we're doing fuzz testing as well as integration testing, and making sure the types that we're using are still what we're expecting them to be. For our second example today is about concurrency. And this one comes from the fruit company that's across the street. If you've done iOS development at all, you probably have seen this button that says Used for Development. Sort of a vague thing. Well, when you connect an iOS device, it's going to ask that device for what the version it's running. And then it's going to pull and find the right developer tools for it. And then it's going to copy those over to the device. When it does this, it's going to also copy over or send over the path to where this file is being stored now. When we are going to go and send over a verify with a signature of this disk image that we just sent over of developer tools, and that is going to then open up that file that we just sent over, verify it against the signature that is packaged with it, and make sure that we're not mounting something that we shouldn't. If it passes this, it's going to then copy the disk image over onto a private staging area. Here, it's not accessible by anything but the image mounting process on the device. And then it's going to mount the disk image. This will install the developer tools onto your device. Now, it may not be apparently clear as to why this is a concurrency problem, so we'll just walk through it and see where things start going weird. So we're going to copy the developer tools over again, verify, but when we start the verify, it's going to open the file system reference on the device. After it does that, we're going to tell the device it should rename the file of the disk image into something else. This preserves the file system reference, so it's not going to be changing or restarting the verify that was already begun. While that's happening, we're going to start copying over our own custom image. So this entire time, the verify is still looking at the original file, thinking it's in the place that we originally told it was. Now we've got a new file in that place. When that verify passes, that custom disk image we made is now going to be copied over instead of the real one. So it's completely unverified, not signed at all, and it's now just gone into a private sandbox on the device. This will now be mounted without verification, and you have now just installed any software you want on your iOS device. So how do you really fix something like this? Same way in Objective-C or with Swift, you've got concurrency and you may have thread unsafe objects. You're going to want to treat your file system like a thread unsafe object, because that can operate underneath you between operations. So while you're checking to make sure your file exists, it could change and not exist by the time you go to open it. So the way that this was fixed was in the latest version of our latest public release. It will now ask the disk image to be sent over directly, and then it will be written into the private staging environment. With this, we're bypassing any access to it from the user, and nothing else can touch it. So the verify can happen uninterrupted. And this one's a bit more tricky to sort of fix in your own code, because how do we test things that aren't really there? With this, it's mainly a lot of verification process and making sure you're mapping files out before you open them. There isn't quite too much you can do other than try to move everything up into memory and then keep it there as long as you can. For this, I was working with two people. A friend of mine, Yakov, who was working with me on finding and fixing the URL parsing bug. This was a few years back. And a friend of mine, WinowCM, for her help in helping me backport the disk image bug to previous versions of iOS. Now, for today, I've prepared a code sample for you at the link at the bottom. And with that contains some source code to C and Swift code of both of these bugs, and to show that even though we've got all the new technology that was released earlier this week, including type safety and handling that we don't have in C, that a lot of the bugs that exist in software aren't inherently because of the language itself, but because of how we are writing code and any sort of oversight that might happen through lack of review. If you want to get in touch with me, my other information is up there, and I'll be doing a lab on Friday if you want to stop by and ask any more questions. This went a bit faster than I was expecting, so I guess I can open the floor to questions, if that's all right. Okay, so
what I didn't understand, what didn't follow, like, why was the disk image being renamed?
all right, so why was the disk image being renamed? If we told the disk image, because we're copying over the disk image to the device, and we tell the verify to start verifying the file at that path, if we then start another operation going alongside it, so a concurrent operation then operating on that to say, hey, this file here, we want to rename it to something else, that will be preserving the inode on the device and the file system reference, so it will not appear to the verify process that anything changed with the file, even though it has. No questions?
If you had a top 5 set of tips for your average Cocoa Mac iOS developer for keeping their code secure, what would you look at?
All right. Definitely verify what you're using and how you're using it. With C and Objective-C, we're using a lot of inferred types, and that's becoming quite apparent with a lot of the stuff that's come out with Swift, is that calls that we thought were going to return like an string might be returning a string type in Swift instead. So type enforcement, wherever you can, verifying what you're working with is what exactly you're working with. A lot of sanity checks are in place, but you have to also then write tests for those, as in the one I talked about, like where that sanity check was what caused the bug and the exploit in that example. So top 5 would probably be getting 5 other people who don't write code like you to read your code, because that will probably make things stand out even more than anything else. Right, I guess there's no other questions then. Oh.
So one of the big strengths of Objective-C that I personally like as a developer, and they're trying to make it even bigger with Swift, is the idea that, like you're saying, there's this whole big inferred type system. Now, personally as a developer, I know I've caught a lot of stupid bugs that happen because I'm using some really basic API, like everyone knows NS dictionary with contents of file and stuff like that. So I'm curious if you've seen like exploits or any instances where those sorts of oversights can actually lead to security vulnerabilities. Or is that just, because obviously we want to avoid crashes, but we probably also want to avoid people introducing, different types of data that we thought we were using.
Yes. With Swift, I think it's a bit too early for me to say one way or another. With Objective-C, though, you can definitely get some very weird behavior due to like a lot of the similar calls against different types of objects. So if you are expecting NS like array, or NS actually would be NS dictionary, and it's actually like NS array, calling count on it, you're going to get a key count or an item count. But then that's going to work on either of them. Operating it again with a specific one would then cause a crash or cause undefined behavior depending on what language or framework you're using. So I would say avoid using like raw C or C++ if you can, because that will turn things a lot more dangerous for you. Using something like Objective-C is safer, even though, and like responds to selector or recognizes selector before calling things can get a bit excessive, but in some cases you might want to do it before serious operations that'll go on for a while, so you're not, so you're getting that additional verification check first.
Hey, when can we expect your book to come out?
I believe sometime later this year. Well, I didn't say that last year. All right, thank you. Time, many years. And we'd like to talk to you about 2 real-world cases of exploitable code that existed in software for one for many years and one for a couple of months that ended up in being quite dangerous for everyone. First comes from a company you may know of as a game studio that can't count up to the number 3, involving input handling, specifically with URL strings. Now, what is a valid URL string? When asked this question, I sort of came up with 3 general.
engineering software. He's currently working on the second edition of OS X Internal's A Systems Approach. Sam Marshall.
Right. Hello. So for my talk, I decided to go with something that's a little bit different from everyone else. Talk about some insecure code. So what exactly does this mean? We've seen over the past few months that a lot of code, especially with cryptography, has had a lot of bugs in it that has resulted in terrible things happening. And a lot of people attribute this to the languages we use and our code review and auditing process. For stuff like OpenSSL and Apple's own security framework, this is true. But I think a lot of the issue is not in so much the languages we use, but in the fact that code is both really hard to do. Even when we're doing simple things, it's very easy to get very complicated within a few minutes of starting. With this, we get mistakes quite often. Some of these go unnoticed for quite a long time.
Hello again. How are y'all doing? All right. Awesome. Good. Glad to hear it. I just wanted to reiterate quickly, one of the purposes of this event is for everyone to be able to come and learn and hang out with each other and be awesome. If for any reason you feel like that's not happening or something weird is happening or you feel unsafe or unwelcome for any reason, just find someone in a blue shirt. They'll help you. And if you can't find someone in a blue shirt, there are people at the front desk who can help you. So our next speaker is an iOS and OS X developer who is known for breaking and reverse engineering